Consider the inflating balloon, they say. If the volume is increasing at a rate of 125 cubic centimeters per second, calculate the rate at which the radius is increasing when the radius measures 10 centimeters. Okay, so the balloon is a sphere, and they want to talk about changes in its volume compared to changes in its radius. So when you have a situation like this, there's going to be two variables changing, in this case their volume and radius, and you need some formula that ties together volume and radius, and there's a pretty obvious one. The volume of a sphere is 4/3 pi times the radius of the sphere cubed. If we have this, if we're talking about changes, especially changes per second, what that means is we're doing what we call a derivative with respect to time, what we write as d dt. And that means two separate things. It means first, differentiate this equation. Second, divide it, both sides of it, by dt. So we can do that. If we do the derivative of v, that's very simple. It's just dv. I'm doing this like an implicit derivative. That's the way that turns out the nicest here. So the derivative of v is dv. And on this side, we have 4/3 pi. All of this is a coefficient. It's kind of a complicated coefficient, and it's got some Greek in it, but still, all this is a constant. And so we see this as a constant times r to the third. We multiply the whole thing by 3, which leaves us with 4 pi. Then we get r to the 2, and the last thing that happens from the chain rule is dr. So this says the change in your volume is going to be 4 pi r squared times the change in your radius. And if those changes are happening per unit time, then we divide the left side by dt and the right side by dt. So now dv dt is how fast your volume is changing. This would be like cubic centimeters per second, which we have. dr dt would be the change in your radius per unit time, so this would be like centimeters per second. So let's see if we can put some numbers into this. dv dt is given. It's 125 cubic centimeters per second, and they say it's increasing, so that's a positive number. Plus 125 equals 4 times pi times, they say the radius is 10 at the point we're looking at, squared. And if we have all that, we can solve for dr dt. dr dt, the rate of change of the radius, is going to be 125 over 4 times pi times 10 squared is 100. And that comes out to divided by pi, almost exactly a tenth. I get 0.99471,839. That's using a lot of decimal places for pi, so approximately 0.1 centimeters per second. I know those are the units because we're using centimeters for our distances and seconds for our time. This one will come out with the same units. So the radius is growing this quickly when the volume is growing this quickly.